Hey everyone, it's Miss Butler. Got a video on the acid-base properties of salts. This will hopefully help you with our Unit 5 objective number 4. Just 3 problems, just some kind of hints for you. Number 127 is really similar to the interactive example on page 585, so check that out before you try it. And then number 123 and 130 require you to look up Ka or Kb values. Just remember, if you can only find the Ka for the acid, Kw, which is 1.0 times 10 to the negative 14th, is equal to Ka times Kb. I just screenshotted some tables that are very similar to our book of Ka values for weak acid, so that might help you with your problem set or some of the problems in this video. And some Kb values for some common weak bases. Again, you might find these helpful. Otherwise, you can always look up the table within the chapters in our book. So one issue we're going to start to run into is that not all substances have an H plus or an OH minus, but that does not mean they can't produce H plus or OH minus when they're in water. So we're really looking at acid and base properties of salts. A salt is an ionic compound. Usually what we focus on in our class is a metal bonded with a nonmetal, but really you can think of a cation, something that's positive charge, bonded with a negatively charged anion, because a lot of salts involve polyatomic ions. So either a negative or a positive polyatomic ion can be part of a salt. What we need to care about is that in our neutralization reactions, where we take an acid plus a base to make water, the neutral part, a salt is also formed. So we're always making a salt when we do our neutralization reactions, acid plus base, we pull out the water, you're making a salt. And that salt may have some acid properties, basic properties, or it could be neutral just like the water. So it could be acidic, basic, or neutral. So let's first talk about neutral salts. So we are making a neutral salt. The cation is going to come in that salt is going to come from a strong base. So it's usually going to be an alkali metal in the group 1A or one of our heavy 2A group, the alkaline earth metals will be our cation. And our anion usually comes from a strong acid. So something like chloride or nitrate, again, like bromide, any of those anions that are usually attached to an H plus in a strong acid. So looking at this example, HCl is one of our strong acids, reacts with NaOH, which is a strong base. So what I see here is we make our HOH, our water. You always pull out the water, so that takes care of the OH and the H plus. That leaves us with chlorine and sodium to make our salt. So what I noticed from this neutral salt is we need to take a peek at this guy right here and see if it has any acid or base properties. The way we do that is we take that salt and we're going to pull it apart and assess if it's acidic, basic, or neutral. So what happens is this is an aqueous salt, so it's going to dissolve into the ions and it could interact with some water. So here's what we have going on. We could have this Na+, the cation, reacting with water to make sodium hydroxide and H+. So it's a single replacement. Think about this as HOH. We're replacing the H out in front with the Na to make NaOH, and then we're left with H+. The only problem with this is a strong base. So the truth is this particular reaction is only going in the reverse direction. So this arrow is actually not happening. We're actually not producing any H+. I don't know if you can see that. That might be out of the screen. Say not formed, okay? So really this is a reaction that's going in the reverse direction. We are not forming that H+, because anytime you have a strong base, it is not going, we know it like breaks apart completely. We're not going to be making H+. The other reaction is our chloride ion reacting with water, and we have the same situation, a strong acid. So this reaction's not happening, we're actually going in the reverse direction. So OH minus is also not produced or not formed. So both of these reactions are recurring in reverse. We're not actually producing H plus, we're not actually producing OH minus, which leads us to this idea that NaCl is a neutral salt. No acidic H plus is produced and no acidic OH minus is produced. So let's look then at a basic salt. Well, if it's a basic salt, the cation is still going to come from a strong base, but the difference here is an anion comes from a weak acid. So really, it's the conjugate base of a weak acid. So in this case, HF is my weak acid. We have NaOH as a strong base. We make our HOH, we pull out our water, and we're left with NaF, which is our salt that we are going to assess if NaF has any acidic or basic properties. So here's how we do this. Same idea, Na plus, it's the same exact reaction that ion interacts with water to make a strong base, which means if that strong base is present, we're actually not going to be producing, we're going to go in the reverse direction. Anytime you have H plus with a strong base, that reaction is just going to go, so we're just going to go in the reverse direction. So in this case, we're actually using up the H plus, it's not going to be produced at all. Okay, but if you look at the next reaction, we have F minus with H2O to make HF. This is a weak acid. So what's really going on is we have a nice equilibrium here. So we are in equilibrium. So this reaction is going back and forth, meaning we are going to produce some OH. So what occurs is our pH could go up because we have a concentration of OH minus being produced, so we become more basic, which means NaF is a basic salt because that F minus is in equilibrium with water and it produces the hydroxide, which makes it a basic salt. Even though NaF does not have an OH minus, it still is basic. So this is a typical question that could be asked, like how basic or what is the pH of this salt? So here's a problem or something similar you might see on a test or a problem set. Calculate the pH of 0.075 molar KCN. So our first thing that we need to look at is the fact that KCN has no proton. So the ions of this guy, there's no H plus, there's no H minus, but if I break it into the ions and have it interact with water, can it produce H plus and OH minus? So let's figure out first what type of salt this is. So we take K plus, interact it with water. Draw my arrow, that's going to make KOH and H plus, excuse me. KOH is a strong base, which means this reaction is only happening in the reverse direction. Okay, so this is not produced. And my next reaction would be CN minus plus water makes HCN plus OH minus. This guy is a weak acid, which means we are in equilibrium, which means this is produced. So first thing I noticed is KCN is a basic salt. Why is it basic? Because we are producing OH minus when the CN minus is in equilibrium with water. So next we need to find the concentration of CN minus. So here's what we need. We know KCN is a strong electrolyte. That just means it is soluble, right? So if I have 0.075 molar KCN, it means I have 0.075 molar of the CN minus. So when we set up our ice table, let me give myself a little more room. Okay, I'm going to set up this ice table. Because I'm able then to find the pH if I can solve for OH minus at equilibrium. So I don't care about the liquid. Okay, hopefully you're feeling all right with our ice tables. If you're not, come see me and I'll give you some help. This guy is a base, so it's a Kb expression. Products divided by our reactants. And so we'll use this idea that Kw is equal to Ka times Kb. They gave me the Ka of HCN, of this guy, so I can find the Kb of Cn minus by taking that number for Ka and dividing it into the Kw value. So I have my Kb. I'm going to go to the next slide where I have a little bit more room. So same exact thing here, and now I'm just going to set everything up. So we get 2.04, which is times 10 to the negative fifth, which is my Kb. And then we're plugging in our E line from the ice table. I'm going to omit that x to make my math a little easier. So I get x squared over 0.075. This allows me to give x as 0.0012, which is my OH minus at equilibrium. So what I'm able to do finally is take the negative log of OH minus to get POH. Which is 2.9. And then I know that 14 equals the pH plus the POH. So 14 minus 2.9 will give me a pH of 11.1. Okay, we can also do the 5% rule really quick. So I'll take my x, 0.0012, over what I omitted it from, times 100, and that is less than 5%. So we are good with our assumption. All right, I also want to talk about acidic salts, same idea. This time the cation is coming from a weak base. That means it is the conjugate acid from the weak base. And then the anion is coming from a strong acid. So let's prove in this example, so again, strong acid, weak base. Let's prove that this salt is actually making something acidic. So I take the ammonium, NH4+, with water. That makes a weak base, so we're in equilibrium. And we have the hydronium, which we know is H+ produced, and that is equilibrium. And then we have our HCl, which is a strong acid. So we know that this reaction is actually happening in the reverse. No OH minus is actually being produced. So that leads us to believe that the NH4Cl is an acidic salt. All right, here's another typical problem. What is the molarity of the CH3COO solution with a pH of 8? And then they give us the Ka value. So I'm just going to kind of walk you guys through this one. I wrote it out ahead of time to save some time. So first, what type of salt is this? Well, we have K+. That's going to be neutral. It comes from KOH, which is a strong base. I'm not going to write that reaction out. But then we have this CH3COO minus. That creates a weak acid. So that means we know we are producing OH minus because we're in equilibrium. So there is some OH minus. This salt is basic. I want to know the initial molarity, and they gave me pH. So what we're ultimately solving for right now is this question mark right here, the starting value. So we're looking for question mark, but luckily they give us the starting pH as 8. And I know that if I find POH, I can take 10 to the negative POH to get my concentration of OH minus at equilibrium. Once I have that, I essentially have X. So if I can plug that into my Kb expression, then I have X, X, and then question mark minus X. That will allow me to solve for question mark. The only trick, again, is they gave us Ka. So if we're using this particular reaction where we're producing the hydroxide, we need a Kb expression. So I take my Kw for water and the Ka that's given and solve for Kb. Once I have that, I can plug in my x value, which is 1 times 10 to the negative 6, here, and here, and solve for question mark. And that question mark represents the starting concentration of the CH3COO minus, which is the same as this guy. All right, and then finally, what happens if both of the ions in the salt are coming from something weak? So for example, I have this guy and this guy. I know that the NH4 is coming from a weak base, ammonium, and so we're making this H plus or hydronium in solution, and we know Cn minus, so this is equilibrium, right? Because we have a weak base. And then Cn minus comes from the weak acid, and so this is also in equilibrium down here, producing OH minus. So what we have to ask ourselves is, since both an acid and a base are produced, is it acidic or basic? Well, we want to know which equilibrium wins. So whichever one favors the products more will determine if it's acidic or basic. So what we look at is we look at the Ka for the NH4 plus, and we look at the Kb for the Cn minus, and what happens is we compare them. So in this case, the Kb value for the Cn minus is larger than the Ka for the NH4 plus. So this means the second equilibrium, this guy right here, favors the products more because the Kb value is bigger. And so if the products are favored more, it means there's more OH minus, which will ultimately result in a basic pH. So NH4Cn is a basic salt because the Kb of Cn minus is larger than the Kb of NH4 plus. Hopefully all of this helps with your problem set. See you after break.